1945, all 21 production racks were operating. Initially the output of S50 was fed into Y12, but starting in March 1945 all three enrichment processes were run in series. S50 became the first stage, enriching uranium from 0.71% to 0.89% uranium-235. This was then fed into the gaseous diffusion process in the K25 plant, which produced a product enriched to about 23%. In turn, this was fed into Y12, 167, which boosted it to about 89%, sufficient for use in nuclear weapons. About 50 kilograms, 110 pounds, of uranium enriched to 89% was delivered to Los Alamos by July 1945. The entire 50 kilograms, along with some 50% enriched, averaging out to about 85% enriched, were used in the first Little Boy bomb. 168. Plutonium. The second line of development pursued by the Manhattan Project used plutonium. Although small amounts of plutonium exist in nature, the best way to obtain large quantities is via reactor. Natural uranium is bombarded by neutrons and transmuted into uranium-239, which rapidly decays, first into neptunium-239 and then into plutonium-239. 169, as only a small amount will be transformed. The plutonium must be chemically separated from the remaining uranium, from any initial impurities, and from fission products. 169, X10 graphite reactor. Two workmen on a movable platform similar to that used by window washers, stick a rod into one of many small holes in the wall in front of them. Workers load uranium slugs into the X10 graphite reactor. In March 1943, DuPont began construction of a plutonium plant on a 112-acre, 0.5 square kilometer, site at Oak Ridge. Intended as a pilot plant for the larger production facilities at Hanford, it included the air-cooled X10 graphite reactor, a chemical separation plant, and support facilities. Because of the subsequent decision to construct water-cooled reactors at Hanford, only the chemical separation plant operated as a true pilot. 170. The X10 graphite reactor consisted of a huge block of graphite, 24 feet, 7.3 m, per side, weighing around 1,500 short tons, 1,400 t, surrounded by 7 feet, 2.1 m, of high density concrete as a radiation shield. 170. The greatest difficulty was encountered with the uranium slugs produced by Mallinckrodt and metal hydrides. These had to be coated in aluminum to avoid corrosion and the escape of fission products into the cooling system. The Grasselli Chemical Company attempted to develop a hot dipping process without success. Alco tried canning, developing a new process for fluxless welding. 97% of the cans passed a standard vacuum test, but high temperature tests indicated a failure rate of more than 50%. Nonetheless, production began in June 1943. The metallurgical laboratory eventually developed an improved welding technique with the help of General Electric, which was incorporated into the production process in October 1943. 171. The X10 graphite reactor went critical on the 4th of November 1943 with about 30 short tons, 27 t, of uranium. A week later the load was increased to 36 short tons, 33 t, raising its power generation to 500 kilowatts, and by feed of the month the first 500 milligrams of plutonium was created. 172. Gradual modifications raised the power to 4,000 kilowatt in July 1944. X-10 operated as a production plant until January 1945, when it was turned over to Research. 173 Hanford reactors. Although an air-cooled design was chosen for the reactor at Oak Ridge to facilitate rapid construction, this would be impractical for the much larger production reactors. Initial designs by the Metallurgical Laboratory and DuPont used helium for cooling, before they determined that a water-cooled reactor would be simpler, cheaper and quicker to build. 174. The design did not become available until the 4th of October, 1943. In the meantime, Mavias concentrated on improving the Hanford site by erecting accommodations, improving the roads, building a railway switch line, and upgrading the electricity, water and telephone lines. 175. An aerial view of the Hanford B reactor site. From June 1944. At center is the reactor building. Small trucks dot the landscape and give a sense of scale. Two large water towers loom above the plant. Aerial view of Hanford B reactor site. June 1944. As at Oak Ridge, the most difficulty was encountered while canning uranium slugs, which commenced at Hanford in March 1944. They were pickled to remove dirt and impurities, dipped in molten bronze, tin, and aluminum silicon alloy, canned using hydraulic presses, and then capped using arc welding under an argon atmosphere. Finally, they were tested to detect holes or faulty welds. Disappointingly, most canned slugs initially failed the tests, resulting in an output of only a handful per day. But steady progress was made, and by June 1944 production increased to the point where it appeared that 10 canned slugs would be available to start Reactor B on schedule in August 1944. 176. Work began on Reactor B, the first of 6 planned 250 MW reactors, on the 10th of October 1943. 177. The reactor complexes were given letter designations A through F, with B, D and F sites developed first, as this maximized the distance between the reactors. They would be the only one constructed during the Manhattan Project. 178. Some 390 short tons, 350 t, of steel, 17,400 cubic yards, 13,300 cubic meters, of concrete, 50,000 concrete blocks and 71,000 concrete bricks were used to construct the 120-foot, 37 m, high building. Construction of the reactor itself commenced in February 1944. 179, watched by Compton, Mavias, DuPont, S. Crawford, Green, Ewald, Leona Woods and Femi, who inserted the first slug. The reactor was powered up beginning on the 13th of September, 1944. Over the next few days, 838 tubes were loaded and the reactor went critical. Shortly after midnight on the 27th of September, the operators began to withdraw the control rods to initiate production. At first all appeared well, but around 3 the power level started to drop and by 6:30 the reactor had shut down completely. The cooling water was investigated to see if there was a leak or contamination. The next day the reactor started up again, only to shut down once more. 180, 181. Femi contacted Jiansheng Wu, who identified the cause of the problem as neutron poisoning from xenon 135, which has a half-life of 9.2 hours. 182. Femi, Woods, Donald J. Hughes and John Archibald Wheelathan calculated the nuclear cross-section of xenon 135, which turned out to be 30,000 times that of uranium. 183. DuPont engineer George Graves had deviated from the Metallurgical Laboratory's original design, in which the reactor had 1,500 tubes arranged in a circle, and had added an additional 504 tubes to fill in the corners. The scientists had originally considered this over-engineering a waste of time and money, but Fermi realized that by loading all 2004 tubes, the reactor could reach the required power.
Yes, we have to stop because the camcorder is out of power. We need to charge the camcorder. So I think I'll do that. Then I will start to cook some hot foods. And we have a very bad weather. We have a storm arriving in Denmark. I will make some pork mix potatoes. I will do that, but I need a little break. I will make this pork meat and potatoes, some brown gravy. So, but first I need a little break. So I will have to read it again because I'm super sleepy. I'm very, very sleepy and that's too much information, but I like to read it. I will have to read it one more time, but I don't have time to do that because I have so many. I have many hundreds others PDF I like to read. But I'm super sleepy today and not remember much, but I like to read it.